So at this point now, we're going to start talking about the collisions in one dimensions. So there is two types of collisions. We can have a collision that happens in two dimensions. So you can see that in this example right here, you have a positive charge particle and the positive charge particles. Then when this particle comes closer to this particle, because the positive and the positive means that you get a repulsive force. So you can see that this is going to move in a curve. And so what this tells me is that as this particle is moving, both x and y are changing. So this would be an example of a collision in two dimensions. Now, a collision in one dimension means that the collision takes place in such a way that the two particles are colliding head on. So you can see this is M1 and this is M2, and the two particles are colliding in such a way that everything takes place in a straight line. And so we're going to derive some equations that are going to let us to solve this type of systems here. All right. So now we can distinguish two types of collisions. The first one is called a perfectly inelastic collision. So in a perfectly inelastic collision, what happens is that before the collision, the two particles are moving separately. Then after the collision, the two particles move together. So it means that you can say that this is M1, this is moving with some velocity V1I. This is M2 moving with some velocity V2I. Then after the two particles get stuck together and they move together with some final velocity. So in this type of problem here, I'm interested in calculating this final velocity right here. So again, if this is an isolated system, there is no external forces acting on the system, I could say that the change in the momentum is just equals to 0. So it means that the change in Pi is equals to the change in P final. So I can write this equation as M1 V1I plus M2 V2I is equals to M1 plus M2 V final. So this is just one equation that would let me to calculate my V final. So V final here is just the momentum, is the velocity of the combined system after the collision. So again, inelastic collision means that the two particles are going to get stuck together and they move together after just as one particle with the final velocity V final that can be calculated from this equation right here. All right. So the second type of collision is called an elastic collision. So in an elastic collision here, you can see that before the collision, the two particles are moving separately. But after the collision, the two particles continue to move separately with new velocities as well. So you can see in this picture here, you have some particle M1 moving with some velocity V1I, and some particle M2 moving with some velocity V2I. And then after the collision, you can see that V1 is moving with some velocity V1 final to the left, and V2 and M2 is moving with some velocity V2 final to the right. So again, in an elastic collision, the two particles will continue to move separately with new velocities. So basically, I can write down two equations here. So the first equation is just to say that the total momentum before is equals to the total momentum after. So M1 V1I plus M2 V2I must be equals to M1 V1 final plus M2 V2 final. Then also I can assume that if there is no external forces acting on the system, then the total energy of the system should not change. And since this collision is taking place in the x direction, so the change in potential energy is 0. So it means that the only energy that I'm interested in here is the kinetic energy. So I could say that the total kinetic energy before must be equals to the total kinetic energy after. So I can rewrite this equation as 1/2 M1 V1I squared plus 1/2 M2 V2I squared is equals to 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. So in a typical problem here, M1 is going to be given, V1I is going to be given, M2 is going to be given, and V2I is going to be given. And the problem is going to ask you to calculate V1 final and V2 final. So again, since we're going to calculate two quantities, V1 final and V2 final, we need two equations, and so we could solve those two equations together to calculate our V1 final and our V2 final. All right. So basically, for elastic collision here, because we know that the kinetic energy before, the sum of the kinetic energy before is equal to the sum of the kinetic energy after. So again, you notice that because there is a factor of half, so this factor of half is going to cancel all throughout. And so I can take this equation here and rewrite it in this form right here. So I can write this as just M1 V1 initial square minus V1 final square is equals to M2 into V2 final square minus V2 initial square. So I'm just rearrange this equation here to get this equation. Now, because again, I can take this and rewrite this in this form here, just because I know that V1 initial square minus V1 final square can be written in this form, and V2 final square minus V2 initial square can also be written in this form like that. All right, but now we know that P1 initial is equals to P1 final, so we know that M1 V1I plus M2 V2I is equals to M1 V1 final plus M2 V2 final. So from here, I can write this as M1 into V1 initial minus V1 final is equals to M2 into V2 final minus V2 initial. So it means that this quantity right here, so M1 into V1 initial minus V1 final is equals to M2 into V2 final minus V2 initial. So it means that this term, the first term here, is going to cancel with this term, and I end up with this equation right here. So it tells me that V1 initial plus V1 final must be equals to V2 final plus V2 initial. And so I can rearrange this equation again and write it as V1 initial minus V2 initial is equals to negative into V1 final minus V2 final. All right, then so basically again, so we can rearrange. So again, so this equation here is my original equation for the conservation of momentum. The second equation is just a rearrangement of the equation for the conservation of energy. So if you solve these two equations together, you derive this simplified equation. So these are the two equations that will let us to calculate my V1 final and my V2 final. So again, you notice that we said that in a typical problem, I'm going to be given what my V1 initial is and what my V2 initial is. And I'm also going to be given my M1 and my M2. So if I know M1 V1 initial, M2 V2 initial, I can calculate my V1 final and my V2 final using these two equations right here. So these are the equations that we're going to be using to solve our collision problems. Again, you can only use these equations here if the problem tells you that this is an elastic collision. All right, so again, we have these equations here, then we can look at, so what happens when M1, so if M1 is equals to M2, then you can notice that when M1 is equals to M2, if you just make M1 equals to M2 here, this first term would be 0, and so you can just get V1 final is equals to V2 final, is equals to V2 initial, and V2 final is equals to V1 initial. So what this is saying is that if you have two masses that are the same, then if M1 is equals to M2, then after collision, there is just a transfer of the energy in such a way that V1 final becomes V2 initial, and V2 final becomes V1 initial. All right. Okay. So this is again the same equations that we started out with. So we can say that, for example, so we've already said that V1 final is equals to M1 minus M2 over M1 plus M2 V1 initial. So for example, if V2 initial is equals to 0, if V2 initial is equals to 0, so we're saying that before the collision, it's only V1 that is moving. So if V2 initial is equals to 0, then I can write my V1 final as that, and my V2 final as this quantity right here. All right. So these are some simplifications here. We don't really need to focus on this, but these are just some approximations. So I will not really focus on this right here. But this is just some additional simplifications that can be made with our equations. All right. Okay. So now let's look at this example right here. So this is example number 9.5. And so we're going to look at the carry collision insurance problem. So suppose that we have a 1800 kilogram car that is stopped at the traffic light and is struck from the rear by a 900 kilogram car. So the two cars become entangled, moving along the same path as that of the originally moving car. If the smaller car were moving at 20 meters per second before the collision, what is the velocity of the entangled cars after the collision? So this is just an example of an inelastic collision. So we said that in an inelastic collision, the two particles get entangled together and move as one unit. So let's see here. So because the change in the momentum is equal to 0, I can say m1 v1 is equal to m1 plus m2 times v2, all of that times v final. And so if I solve for v final, I get this equation right here. So after the collision, the two systems gets entangled and they move with this combined velocity of 6.67 meters per second. Now suppose that we exchange the masses of the cars. So what if a stationary 900 kilogram car is struck by a moving 1800 kilogram car? Is the final speed the same as before? So let's see. So the final speed is going to be higher, and we can do this. So we just get our v final is m1 v1 over m1 plus m2. So again, if you plug everything there, you get a final speed that is 13.3 meters per second. All right. So now we're going to look at one example right here. So again, this is an example of example number 9.6. This is called the ballistic pendulum. So this is a ballistic pendulum here. So it contains, so M2 is the pendulum and M1 is my projectile. And this M1 has a velocity that's called V1A. So when M1 strikes the projectile, it's going to penetrate the projectile and get stuck in it. So you can see that after this is M1 plus M2, so this is the mass of the pendulum plus the mass of the bullet. And so the kinetic energy is going to be transferred into potential energy of the combined system. So the combined system is the mass of the bullet plus the mass of the projectile. And everything here is going to rise to some final height, which we call h. So again, we can do conservation of, because the first process is an inelastic collision, I can say that the velocity of the bullet is given by this equation right here. So if you rearrange this, you can write this as this, because we know that the velocity of the pendulum is just 0. So it means that V2A is 0. This is not moving. Then if I conserve kinetic energy of the system, so I can say that the kinetic energy of the system is equals to 1/2 m1 plus m2 vb squared. And then if we do some conservation of energy right here, we end up with this final equation here. So we can see that V1A is equals to m1 plus m2 over m1 times 2 times gravity times height. So this is just to conserve, so we're saying that the kinetic energy of the system eventually gets converted into the potential energy of the system. So rearranging that equation, I can solve for the final velocity.